Today we will discuss on an important topic on partial differentiation named Euler's theorem on homogeneous function. So at first we will know what is a homogeneous function. A function fxy in the variables x and y is a homogeneous function if the sum of the powers of xy is same in every term. That is, if f x comma y equals to x square plus 2xy plus y square. Here we can see that the power of x is 2, the power of x in xy is 1 and power of y in xy is 1. So the sum of the powers of in the term xy is also 2 and the sum and the power of y is also 2. So fxy is a homogeneous function of degree 2. Now we will discuss the Euler's theorem on a homogeneous function fx comma y. It is the statement of the theorem. If u equals to fx comma y is a homogeneous function of x and y of degree n, then x into del f by del x plus y into del f by del y equals to nf equals to nu. Now we will give an example. Let u equals to x square plus y square. So here u is a homogeneous function. The degree of each term is n equals to 2. So as per the Euler's theorem, x into del u by del x plus y into del u by del y equals to nu, that is equals to 2u. Now we will verify the result. Here del u by del x, that is partial derivative of u with respect to x, will be the derivative of x square will be 2x and y square will be 0, that is will be 2x. We know that when we differentiate u with respect to del x, then y square will act as a constant. So del u by del x equals to 2x plus 0, that will be 2x, and del u by del y will be 0 plus 2y, that will be 2y. Now putting the values of del u del x and del u del y, we will get x into del u del x plus y into del u del y will be x into 2x plus y into 2y, that will be 2x square plus 2y square, that will be 2 into x square plus y square equals to 2 into u. So here we can see that x into del u del x plus y into del u del y equals to 2y. So here Euler's theorem is verified. Now we will solve some problems related to Euler's theorem. Now here the first problem is, if u equals to xy by x minus y, then show that x into del u del x plus y into del u del y equals to y. Now here u equals to xy divided by x minus y equals to, we can write it as x square into y by x divided by x into 1 minus y by x. That is x into y by x by 1 minus y by x. Here the degree of y by x is, degree of y is 1, degree of x is 1, so both will be cancelled. So degree of y by x will be 0. So it has the degree 0 and x has a degree 1, so the total degree of the function is 1. So we can write it as x into function of y by x, x to the power 1 into function of y by x. So the degree of the function u is 1. So from Euler's theorem we will get x into del u del x plus y into del u del y equals to nu. That here n equals to 1 as the degree is 1, so this will be equals to 1 u, that equals to u. So x del u del x plus y del u del y equals to u is proved. Now the second problem. Here the given function is u equals to x square minus y square divided by xy. So if we take common x square from the numerator, then it will be x square into 1 minus y square by x square, and we take common x square from the denominator, then the denominator will be x square into y by x. So we can write it as x to the power 0 f y by x. Here the degree of u is 0, so from Euler's theorem x into del u del x plus y into del u del y equals to nu. Here n equals to 0, so 0 into u will be 0. From Euler's theorem. Now the third question is, if u equals to x square plus y square divided by root over x plus y, then prove that x into del u by del x plus y into del u by del y equals to 3 by 2 into y. Now here u equals to x square plus y square divided by root over x plus y. So we will take common x square from the numerator, so the numerator will be x square into y square by x square, and the denominator will be root x. If we take root x common from the denominator, then the denominator will be 1 plus root over y by x. So it is a function, we know that root x equals to x to the power half. Root x equals to x to the power half. So the total power x will be x to the power 2 minus half into function of y by x. So it will be x to the power 3 by 2 into function of y by x. So here n equals to 3 by 2. N is the degree of the polynomial, degree of the function ux comma y. So here n equals to 3 by 2. So from Euler's theorem we will get x into del u del x plus y into del u del y equals to 3 by 2 into u. Now the fourth question is, if u equals to sin inverse x minus y divided by root x plus root y, then prove that x del u del x plus y del u del y equals to half tan u. Now here u is sin inverse x minus y divided by root over x plus root over y. Now here the x minus y by root over x plus root over y term is under sin inverse. So at first we will bring the sin inverse to the left side, then the equation will be sin u equals to x minus y by root over x plus root over y equals to vx comma y. We take x minus y by root x plus root y equals to v. Now v equals to x minus y by root x plus root y. If we take x common from the numerator will be x into 1 minus y by x, and the denominator will be root x into 1 plus root over y by x. So it will be x to the power half So fy by x. Clearly, here v is a homogeneous function of degree half. So here n equals to half for v. So from Euler's theorem on v, we will get x into del v del x plus y into del v del y equals to half v. Now in the question we have to prove x del u del x plus y del u del y equals to half tan u. So we have to find the value of del v del x and del v del y. Now here v equals to sin u or del v del x equals to del v del u into del u del x. Here del v del u equals to cos u. We know the derivative of sin u is cos u into del u del x. Similarly, del v del y equals to del v del u into del u del y. Del v del u equals to cos u into del u del y. Putting the values, we will get x into cos u del u del x plus y into cos u del u del y equals to half sin u. Now if we divide the whole equation by cos u, the equation will be x del u del x plus y del u del y equals to half sin u by cos u, that is half tan u. So our question is solved, as we have proved that x del u del x plus y del u del y equals to half tan u.